What makes a car more powerful, faster, and at the same time more economical and environmentally friendly? If you think it's just the engine, it's not entirely true. To get speed and power, the best solution isn't necessarily to cram a larger engine under the hood. An alternative is to add a turbocharger. But did you know that in addition to turbocharging, an internal combustion engine can also be supercharged? What's a supercharger and how is it different from a turbocharger? We'll find out today. First, let's do a quick rundown on turbochargers. You might assume a turbocharger is huge and heavy, but actually it's quite small. When it comes to turbochargers, there are two main components, the turbine and the compressor. A turbine is a small impeller, which is a wheel or rotor, that rotates due to the engine exhaust gases. The impeller is connected to the compressor by one shaft. The compressor is also an impeller, but its purpose is to capture and compress the air with its blades. When the engine exhaust rotates the turbine blades, the compressor impeller blades also automatically rotate since they're on the same axis. Outside air is pulled in by the compressor impeller towards the engine cylinders for combustion. A very powerful explosion occurs in the combustion chamber, making the piston turn the crankshaft with greater force. And that's how even a small engine can have high power. In ordinary cars, a turbo can increase the engine's power by 20 to 25% and acceleration by 2 times. In addition to increasing the power, turbocharging allows you to economically use fuel and reduce the toxicity of the exhaust due to the fuel being completely burned in the process. But there's one drawback, turbo lag. When you press the accelerator pedal to pass another car, you need to accelerate quickly, but it might not happen instantaneously. But why does this happen? For the piston to start working with greater force and produce more acceleration, a more powerful explosion needs to occur in the cylinder. This can happen if the fuel-air mixture is enriched with cold compressed air, which gets pumped by the compressor. Since the compressor is fixed on the same shaft as the turbine must first rotate faster. When you press the pedal to the floor, more fuel enters the chamber, but the level of saturation of the fuel-air mixture doesn't increase. So the fuel in the cylinder will not burn out completely, which means you don't get the power and acceleration you expected. Also, it takes time for the fuel to reach the required volume in the combustion chamber, burn out, and for exhaust gases to rotate the turbine at the needed speed. So this delay in response to wide open throttle is called turbo lag. One way to address this issue is to install 2 turbochargers of different sizes. The larger one runs at higher RPMs, while the smaller one operates at lower RPMs. The reason for this setup is because a small turbine by itself can spin faster, but at higher RPMs, it can't effectively handle the volume of compressed air. That's why you have the larger turbo. The result is smooth acceleration dynamics without turbo lag. This is a type of bi-turbo or twin-turbo setup called sequential turbocharging. It's designed to give your engine the needed boost to deliver faster acceleration and avoid turbo lag. For a more detailed explanation, check out my video on turbochargers. But there's an alternative to turbochargers, and that's the supercharger. A supercharger doesn't have a turbine, and it's not driven by the car's own exhaust gases. Instead, it's mechanically driven by belts that are driven by the engine. You have an air pump directly connected to the engine crankshaft by a belt or chain. It always turns and responds immediately to throttle, so you can immediately feel the engine's response when you press the gas. There's practically no delay, and power comes immediately. That's because the air compressor instantly receives the same RPM as the car's crankshaft at any moment. The more you press the gas, the faster the compressor spins. That's one of the key advantages of superchargers over turbos. Let's talk about 3 main types of superchargers: roots, twin screw, and centrifugal. The main difference between these types is how they move air to the intake manifold. Roots and twin screw superchargers draw air in by the use of different types of meshing lobes, where the centrifugal supercharger uses an impeller. All 3 types give your car a boost, but they differ in size and efficiency. Let's dive in and take a look at each. The Roots supercharger is the oldest design. It's named after Francis and Philander Roots. Back in 1860 in Indiana, the Roots brothers founded the Root Blower Company. They patented the Root Blower, which was an air pump used in blast furnaces to blow compressed air to melt iron and for other industrial applications. Pretty much, the Roots supercharger has an oval-shaped body and two rotors that rotate in opposite directions in a cross-section similar to the rotors in an airplane engine. The rotors are mounted on an axle and are located one above the other. When one rotator rotates to the right, the other rotates to the left. As a result, the air is compressed, not inside the compressor, but in the intake manifold. That's why they're sometimes referred to as external compressor. This method allows more fuel to be injected into the combustion chamber and generate more power as the mixture gets enriched with more oxygen. Roots superchargers are popular in muscle cars and hot rods. You can see the part of the supercharger sticking out of the hood because the superchargers sit on top of the engine. But they're the least efficient of the superchargers. One reason is because they're large and add weight to the car. Also, they move air in discrete bursts rather than a continuous smooth flow. The twin-screw supercharger, like Lysom, for the first time, a patent for a screw-type compressor was received by Heinrich Krieger from Germany on March 24, 1878. Unfortunately, the lack of technology at that time did not allow Heinrich to achieve mass production of the screw compressor. But almost half a century later, in 1935, Alf Lysom, who worked for Lundström's Ankturbine AB, later known as Svenska Rotor Maskiner AB or SRM, in 1951, patented a design with rotor wrapping around each other. This kind of supercharger is similar to an auger or corkscrew drill in a traditional meat grinder, like the one Grandma used. However, in this supercharger, two augers or corkscrews work together simultaneously. Instead of compressing air in the intake manifold, the twin-screw supercharger compresses the air inside the body itself. The rotors capture the incoming air and begin a mutual counter-rotation. Then the air is pushed forward like meat in a meat grinder. The twin-screw supercharger is more efficient than the root superchargers, but it's harder and more costly to make, and therefore more expensive to buy. The reason is because the rotors have extremely small clearance between each other, so it requires a higher degree of precision to manufacture correctly. That's one of the main drawbacks, and also why we don't see as many of the twin-screw superchargers in many mass-produced vehicles. They also make more noise, so you need noise suppression techniques. The centrifugal supercharger powers an impeller at high speeds, often more than 50,000 RPMs, to quickly draw air into the compressor. It's kind of like what the fan in your bathroom does when you take a hot, steamy shower. It provides ventilation for the steam to blow out of the room. Centrifugal superchargers are the most efficient of the three types. They're also small, lightweight, and attached to the front of the engine rather than the top. That's why it's the most common of all forced induction systems. The main difference between superchargers and turbochargers is that superchargers have smoother acceleration, better power dynamics, and no turbo lag. But the main disadvantage is that they're fuel hungry. That's the tipping scale today. The average person is more interested in fuel economy than just power alone. Federal requirements for ever improving fuel efficiency, stringent greenhouse gas emission standards, and customers' desire for fuel economy are moving automakers to prefer turbos over superchargers. For example, the global information company IHS Markit found that 220 car models offered a turbocharged engine in 2018 compared to just 30 models with a supercharged engine. Many consumers prefer the lesser of the two evils. They'd rather put up with turbo lag and lack of immediate acceleration rather than spending more gas money on supercharged engine. Besides, turbochargers are more efficient than superchargers since your engine doesn't need to work harder to power the turbo, since it capitalizes on the, in quotation marks, free energy that would otherwise be lost in the exhaust. But some car makers like Volvo, for example, decided not to choose between the two technologies. Instead, they're opting to use both a turbo and a supercharger in new models. For example, the new Drive E engines in their S90 and XC60 models. Some Volvos use a small supercharger to boost power, and the turbo takes over after it spools up. You can see how it's called twin charging. A recent alternative to increasing power involves using an electric supercharged engine that works in conjunction with the turbocharger. In electric supercharging, the compressor rotates with the help of a small electric motor. and it is located between the turbine and the compressor. This small but powerful electric motor is powered by a 48-volt power grid and is capable of spinning up to 170,000 RPMs. It operates almost instantly when you press the gas pedal, without waiting for the flow of exhaust gases to accelerate the turbine wheel. To spin the impeller up to working 65 to 70,000 rotations per minute, the electric motor needs only 250 milliseconds. When you no longer need the electric superchargers, it turns off, in contrast to the continuous operation of the turbine. So the electric motor compensates for turbo lag. The world of cars does not stand still. Engineering technology is progressive and never-ending. Although turbos are winning now, this doesn't mean the age of the supercharger is over. People who like turbochargers love the boost it gives their engine. Large turbos give you high top-end power, but one downside is that they're much more laggy, meaning there's a delay before you achieve full throttle and boost in torque. The reason is because the larger the turbine wheel, the greater the rotational inertia, which means more time is needed to spin its wheel. Let's say you're rally racing or drifting. You let off the gas for a moment, the turbine slows down, so then you press the gas, but you don't get immediate boost. You need to gas again and again or do something else to get the turbine back to working speed. But you're losing time. And why? Because the moment you squeeze the clutch to change gear, you remove your foot off the accelerator. This means that the throttle valve at this moment closes the intake system, and the fuel-air mixture loses its richness and oxygen. Less oxygen, so less force of explosion in the cylinder, which means less torque, hence the slowdown in speed. And when you press the gas again, it's like the turbine is saying, wait a minute, let me think about it. But you want immediate response to the pressed pedal without any delays or hesitation. And while yours is still thinking, a competing car with an explosive bang passes by you. And that's because of his anti-lag system, which minimizes his turbo lag time so that he can press his gas and get immediate boost. The anti-lag system, or ALS, requires an air bypass and ignites a mixture of air and fuel in the exhaust manifold or turbine housing, and not in the engine cylinders. That's the secret sauce behind ALS. Okay, now, wait a minute. To understand ALS, we need to briefly rewind and recall how a conventional turbocharged engine works. So the fuel-air mixture explodes when the piston is close to its maximum top dead center. Thanks to this, we get the most efficient combustion of fuel, and the engine produces the greatest power. When, during the exhaust stroke, the piston ejects the burnt mixture from the cylinder through the exhaust valve, it passes through the turbine wheel and therefore spins it. The turbine wheel, in turn, transfers inertia to the compressor, which forces pressurized air into the combustion chambers of the cylinders. The intercooler also helps to further compress the air before it enters the cylinders. It cools the ambient air before feeding it to the engine. This allows even more air to be fed into the cylinder in one cycle because chilled air is more dense and takes up less space. The result is that a more powerful explosion happens in the combustion chamber of the cylinder. More boom, which means more power. But this is only as long as the driver is pressing the gas. As soon as he lets off the gas, the throttle valve slams shut like a door, and as a result, the turbine doesn't get fed and loses spinning speed. To avoid turbo lag, you need a way for the turbine to not lose its spinning speed. One method to achieve this is to cause an explosion directly in the outlet manifold right in front of the turbine. This type of anti-lag system is called throttle bypass or throttle kick. This is how it works. When you let off the gas, sensors transmit information to the Engine Electronic Control Unit, or ECU. As a result, the anti-lag system shifts the ignition angle towards the delay by 40 degrees or more. Then the injection control system changes the composition of the fuel-air mixture, enriching it with oxygen. At the same time, the throttle valve is constantly kept open by 30%. When the piston already drops down to the bottom dead center, then the spark plug ignition delay is triggered and the exhaust stroke begins. This re-enriched mixture is not yet burned out completely, so all this mixture ready to explode is pushed through the valve into the exhaust manifold. There, on contact with the hot pipes of the exhaust manifold, the remaining fuel explodes. Naturally, combustion continues in the cylinder so the engine doesn't stall. The main volume burns out already in the release. As a result, these explosions maintain high pressure and accelerate the turbine's rotation, even when the throttle valve is nearly closed. In other words, no slowdown in turbine at low engine speeds, and therefore, no need to try to get the turbine back up to a higher speed. And now, when you press the gas again, the fuel ignition advance angle returns to the desired parameters, and your car doesn't experience turbo lag. Immediate acceleration. Anti-lag systems were first used in the early days of turbocharged cars in Formula One racing, around the mid to late 1980s, until fuel restrictions made its use unusable. It later became common in rally cars due to the increased turbo lag from the mandatory restrictor at the intake manifold. Anyway, all this would be all very good if it weren't so bad, because there's one problem. Since our fuel burns practically in the outlet, all this heats up to incredible temperatures. The additional emissions and even higher temperatures places a heavy load on the entire exhaust manifold and the turbine. In fact, it's so damaging that racing cars in the World Rally Championship typically need to replace their turbos after every single race. And that's not cheap. How'd you like to have to change yours after every time you drove the car? Actually, the system isn't very reliable either. But if you want to win the race, then why not? What about ALS in a regular passenger car? How many miles do you think the turbo can handle? Maybe 1,000 miles? Nope, too many zeros. Maybe 100? Still too much. After all, with an ALS, the temperature of the turbine wheel can reach 2,000 degrees Fahrenheit. That's why we see ALS usually in race or performance cars, and why production vehicles with turbocharged engines don't come pre-packaged with ALS. Another type of ALS is the secondary air injection or inlet bypass. You see this often in rally cars like WRC vehicles. In essence, it uses a throttle bypass, which looks like this. A special bypass valve is placed directly in front of the throttle valve, which directs air from the compressor through the intercooler directly into the exhaust manifold, bypassing the engine. The wastegate valve is solenoid controlled, so it accurately controls airflow, while the ECU delivers the correct fuel mixture. All this will be done by the control unit, depending on the conditions that you need to enable anti-lag. That is, now the turbine will blow into itself through the exhaust manifold. Sounds like a great idea, right? With this system, when you let off the gas, the throttle valve closes, but the fuel-air mixture remains enriched by the bypass valve. So the ignition timing is no longer rolled back so much because we provide a certain amount of air to the manifold past the engine. And it continues working while the enriched mixture burns out the exhaust manifold and spins the turbine. Of course, it will be hot there again, but not as hot as the first type of ALS, because fresh air enters the exhaust manifold bypassing the engine, and so it is not as hot. Also, we don't overheat the engine much because we don't roll back the ignition angle much, and the mixture doesn't get enriched as much. So in principle, the setup is much cooler. And that's how this ALS works in many modern racing cars. The turbine blows into itself. Today, modern race cars have special systems that control the various aggressiveness settings in the anti-lag system. This allows the driver to select the appropriate throttle response based on conditions and terrain. In general, they can be divided into two groups, soft and aggressive. The ones used in Toyota and Mitsubishi race cars are quieter compared to those used in Ford and Subaru cars, which have high noise levels and aggressiveness. Okay, so now you're a bit familiar with ALS. So when you see two cars racing simultaneously shooting from the exhaust pipe with flame and roar, you might think, here it is, anti-lag. But don't jump to conclusions. Maybe it's the two-stage rev limiter working. How's that? The engine needs a rev limiter to prevent damage to engine components from overspeeding. This system limits the maximum RPM that an engine crankshaft can reach to reduce damage and failure. The explosions of diesel engines can be especially appealing. Heavy pistons can break the connecting rods, pierce through the engine, demolish the cylinder head, or punch the engine block with fragments of the connecting rod. That's why the limiter stops the rotational speed from going beyond what the engine can physically withstand. This limitation or cutoff consists of two different maximum rotation limits. The first is usually below the red line of the tachometer. Basically, it's the launch control, which is the launch procedure. Its operating principle is based on the car engine's ability to maintain torque when the throttle is open and the clutch is squeezed to the maximum. At this moment of ignition, when the engine reaches a large number of revolutions, the driver stops holding the clutch pedal and the launch control button. This lifts the speed limit and instantly increases torque. Therefore, the first RPM limit is set to ensure optimum grip at the start. The second one is located at the edge of the red field and is just so that the engine doesn't run out of gear. So when you add gas and approach one of the two rev limiters, the car begins a safety procedure, like turning off the fuel or closing the throttle. Since the computer also controls the ignition delay of the mixture, like the anti-lag, where does the on-burn fuel from the cylinders go? That's right, into the exhaust manifold, directly into the turbine, and that's how you get the bang bang, the pop and exhaust flames. Throttle control and anti-lag might appear similar, but they're two separate systems and it can sometimes confuse people. Let's talk about the shock absorber. Many people know what it is, but not everyone knows how they work or the different types of shock absorbers that exist. The shock absorber is the key element of the car's suspension. It's designed to compensate for the load on the chassis when you drive on uneven roads. They dampen the vibrations and prevent the car from rocking, but they're also directly responsible for helping ensure the wheels maintain contact on the road. For example, when you start your engine, the system tilts your car a bit backwards. This relieves the front of the car to reduce the front wheel's contact with the ground. When you brake, the opposite occurs. The body tilts forward to reduce the rear wheel's contact on the ground. And when you turn, the shock absorbers transfer the load to the opposite side of the vehicle. So you can see how it maximizes driver comfort and also keeps the body of your car in a stable horizontal position to prevent it from swinging or rocking. So let's talk about shock absorber design, signs of failure, and replacement options. And then we'll look at some popular myths. The hydraulic shock is the traditional type, and it's the simplest of all. You have oil in a reservoir. The piston causes the oil to flow from one plane of the reservoir to the other. Hydraulic shock can have one or two tubes. The monotube consists of a cylinder body with rod and piston. The entire interior of the cylinder is filled with oil. The piston has overflow holes with valves. When a car wheel hits an uneven surface, the unsprung part of the suspension presses from below on the shock absorber. At the same time, the shock absorber rod begins to lower. When the rod moves, oil flows through the valves in the piston from one cavity to another. This dampens the vibrations of the springs. The basic twin-tube shock absorber consists of two nested cylindrical tubes, an inner tube, which is also called the working tube or pressure tube, and the outer tube, which is called the reserve tube. At the inside bottom, there's a compression valve. When compressed, the oil flows from the inner tube to the outer one. Some people might think the hydraulic shock is outdated, but nevertheless, it's still quite popular for the average driver. That's because it's sturdy enough to create an excellent comfort at speeds ranging from 25 to 45 miles an hour on a flat road. And even if you drive on uneven roads, it can perfectly swallow bumps. But if the speed is faster than that, then its effectiveness and efficiency decreases. For example, if you make a right turn at a speed over 50 miles an hour, your vehicle's left suspension will sag severely, and the car's handling at this moment won't be so good. And in fact, you could fall into a ditch. So why does this type of shock absorber not work in such a critical situation? When a load is placed on one or another part of a car's suspension with hydraulic shock absorbers, the rod of the shock goes down and compression starts. In this case, the oil in its flask begins to pass through the piston with bypass valves from one cavity to another. This dampens the vibrations of the vehicle body and springs. Point is, oil in the shock absorber doesn't create conditions for the rebound mode. That is, the rod won't automatically return to its original state because of the compressed oil. The rod should be pulled back by the spring. Yes, an oil shock absorber absorbs shock from the vibration, but it cannot absorb its own. So when the car turns at a fairly high speed, the shock and its spring experience the maximum pressure of the body. The spring simply can't squeeze the rod back because of the large load acting on it. As a result, it's very difficult to keep the car on track without it flying out. The same thing happens when sudden braking. The back or front of the car will pet, and the reason is that the shock only works with compression, and the rebound happens due to the spring action. You can try it yourself. If you push down on the rod of the shock, it will go down effortlessly into the body, but it'll never come back up. It just has nothing to pull the rod back. This is the first disadvantage of the hydraulic shock. The second disadvantage is that it increases the temperature of the oil inside because of the springing moment during compression and expansion. It can even boil from high pressure and friction, causing cavitation effect. Cavitation is when rapid pressure changes in liquid cause the formation of small vapor-filled cavities in places where the pressure is relatively low. When a bubble collapses or bursts, it produces a shock wave that causes incremental erosion and damage to the metal parts inside. This is especially noticeable on old propellers of ships and boats, where you can clearly see the jagged edges and chipped surfaces. And imagine, that's all from simple bubbles. What about in shock absorbers? Of course, the pistons and sealing elements get damaged, which leads to failure of suspension systems. Also, these systems are dependent on weather conditions, especially severe temperature changes. In cold weather, the oil thickens, which significantly affects the quality of the shock absorbers. The suspension will be quite stiff, but only until the oil warms up. Another type of shock absorber is the gas-filled shock absorber. Some people think that it's filled exclusively with gas without any oil, but that's not true. It usually contains nitrogen gas under pressure, but it also has oil. Oil is the main shock absorbing component of any damper. In addition, it lubricates the O-rings, rubber oil seals, and the piston itself, thereby extending their life. Gas alone simply can't do this on its own. A gas-filled shock consists of a cylinder, a piston rod, and a floating piston, which is installed at the bottom of the shock and divides the cylinder into two parts, which prevents gas and oil from mixing. Near the bottom, under the floating piston, is a pressurized gas reservoir. The pressure there can reach up to 30 atmospheres. The cavity above the floating piston is filled with oil. It's also divided into two sections by a piston, valve, and shaft. A monotube gas shock works according to the same principle. When the damper rod under load begins to drop to the bottom, the oil begins to flow through the calibration holes in the piston into the upper cylinder cavity. When the oil piston touches the gas floating piston, it starts to push it towards the bottom of the damper. But due to the high gas pressure, rebound occurs and the shock absorber rod comes out. Thus, the rod is pulled back not only by the spring, but also by the pressure of the compressed gas. The same gas delays the oil from foaming. It causes practically no cavitation effect and allows the shocks to work with stability under intense loads. This type of shock absorber is tough and is used in vehicles that need maximum suspension. For example, in racing cars or vehicles that drive off-road at full speed. The purpose of this type of shock absorber is to stabilize the car body in the shortest possible time. Gas shocks provide excellent stability for the car on the track, especially if you need to corner at 75 miles an hour with little or no roll. They give the car excellent handling, and it also means the car can have a very short braking distance, but they're also very stiff. For example, you can't squeeze its rod by hand because they're made for the load and inertia of the car's body and that heavy weight. If you were to install such a gas shock on a regular car, then you'd likely feel every pebble under the wheel, every bump or pothole, since it's sensitive. And driving a regular car with this type of shock might be similar to driving a wagon or a carriage. The twin-tube gas shock absorber consists of compensation chamber filled with gas, which reduces the chance of the bottom breaking down due to excessive load. This is in principle the same gas damper, except its body doesn't consist of one cylinder but two, and the gas on the outer chamber has about 4 to 8 atmospheres, not 20 to 30 atmospheres. When the rod in the inner chamber begins to descend, the piston presses on a special valve in the gas chamber. Oil, through this valve, passes into an external chamber in the upper part, which contains nitrogen. Since the gas pressure isn't too high, the rebound of the rod doesn't occur as quickly as in a pure gas shock. This simultaneously provides a comfortable driving experience and at the same time allows the car to be more stable on the road than a car with simple hydraulic shocks. It produces no cavitation effect and oil doesn't boil, which means it is durable. This is a shock for the city, for the track, and for the trip to the ranch. Well, we talked about the type of shock absorbers, but how do you know when it's time to replace them? Shock absorbers can be difficult to diagnose when they're working properly, but when they're bad, you'll know it. Some people think that when there's an oil leak, that's the time to change them, but a dry shock doesn't necessarily guarantee that it's in good condition either. For example, let's say you don't see an external oil leak. This means the cylinder or housing isn't broken, but lack of an oil leak doesn't mean that the piston or something else inside is not damaged. A knocking sound from the shock is also a bad indicator and means that replacement is already quite late. So, the best diagnosis is a subjective sense of the driver. Body swing, loss of stability, pecking during acceleration and braking, frequent ABS activation. All these are signs that your car's dampers are already having problems. By the way, don't think that if one shock needs replacement that you can do just one. Shock absorbers should be replaced in pairs. If you enjoyed this video, please share it. Thank you.